Welcome to Innovate and React. Today I'm very happy to have Florian Nestler, and he is a scientific advisor at Fraunhofer ISE, and we will be discussing the synthesis of methanol and energy carriers. But first of all, maybe give me a short background.
Yeah, hello, Kevin. Thanks for the introduction and for the invite to your podcast. I'm happy to be here. I'm scientific advisor in my department, Sustainable Synthesis Products, at Fraunhofer Institute for Solar Energy Systems, ISE, in Freiburg. And yeah, the Fraunhofer ISE is one of 76 institutes all over Germany. And our institute mainly focuses on photovoltaic. This was basically, as you can already tell from the name of the institute, this is the main research focus. But we also deal with heat pumps, with power electronics, and also integrated photovoltaics. And finally, my division is dealing with hydrogen technologies. And in this division, hydrogen technologies, we have three departments. So one is dealing with electrolysis, so the generation of hydrogen from water. The other is dealing with fuel cells, so the utilization mainly in the mobility sector of hydrogen. And my department, Sustainable Synthesis Processes, is dealing with the synthesis of hydrogen-derived products, such as ammonia, methanol, higher hydrocarbons, and everything you basically need to have a defossilized chemical industry.
Oh, interesting. A broad range of technologies and also products from the chemical side.
Exactly, but it's still quite nice because this whole energy storage concept and is of course also a topic for my colleagues from the photovoltaic departments and also for the energy system department. So they are, I think, pretty happy that they have the expertise in-house with us, that we can tell them, okay, how can we store energy in a chemical way? What is the most recent technology improvements in this sector? And how can they implement this into their model?
Yeah, the more renewable energy we have in our energy system, the more energy storage we need. And
Yeah.
this is what we will be talking today about. Yeah, hydrogen is a really hot topic at the moment, although I would say the hype has decreased a bit, but still it will be a very important part in the future energy system. And maybe we can shortly introduce hydrogen. Why is it such an important piece of the future energy system?
Yes, the hype has declined a bit, I would say. It's not over, and I would say this was also due to some politics in Germany. I think there will be new publicly funded projects soon, very interesting topics, which are still open for research. And yeah, hydrogen is going to be the basic molecule for our energy transition. Hydrogen we can produce from water electrolysis, which is driven by renewable energies. Renewable energy is, of course, always a topic. Here in Germany, we will not have enough renewable energy to supply all our hydrogen demands. So basically, yeah, we will need to import hydrogen carriers and also energy carriers, which usually contain hydrogen, to Europe and to Germany. That's more or less the field I'm working in. So I'm looking for carbon-based and nitrogen-based fuels and chemicals. So as hydrogen carriers, really as platform chemicals, but also as direct application as fuel, for example, for maritime or aviation industry.
There, the demand will really increase. I guess there were in the past few months a lot of media coverage about the shipping industry and also the aviation industry, really focusing on synthetic air fuels and also methanol or ammonia as fuels for the ships, which will also drive a huge demand. If you think about how much fuel those sectors consume, that even the small percentages will already give a really big demand.
Definitely. Indeed, these sectors are like the first movers when it comes to also green methanol, but also green ammonia. The shipping industry is, I would say, even further than the aviation industry. Sustainable aviation fuels are currently rather made via biogenic pathways, so based on ethanol, this HEFA route, but also there's a lot of activities in Fischer-Tropsch related sustainable aviation fuels and also methanol-based sustainable aviation fuels. And of course, for the shipping industry, there are a lot of announcements by like big companies like Maersk, for
Yeah.
example, who are now transforming their whole fleet to green methanol or ammonia or multi-fuel approaches also out there. This is very interesting to observe, and this is indeed the first market for these green molecules. Yeah.
Yeah, definitely. Because hydrogen will be the way of converting electrical energy from renewable sources into a molecule, but hydrogen has a bit of a problem with storage because it's a gas and not as easily to handle like a liquid, for example. And in the liquid form, we have all these carbon based molecules, and ammonia is, yeah, when you store it, I think it's also liquid. So, what would be the hydrogen carriers which are carbon based?
Mhm. That's a good question. Well, actually, you can think of any molecule, any hydrocarbon out there. Everything can be a carbon-based hydrogen carrier. Of course, when we talk about energy carriers, like by means of gravimetric heating value, hydrogen is the best molecule we can obtain.
Yeah.
But as you said, when it's about volume, then we don't want to talk about hydrogen because then you would need, even with compressed hydrogen to 700 bar or minus 253 degrees Celsius, liquefied hydrogen, you would need a lot of volume to store a significant amount of energy. So for these applications, we will need these carbon-based fuels. And on the other hand, as hydrogen is so difficult to store, we will also need these carbon-based hydrogen carriers like methanol. You could also talk about methane in that case. Methane, again, has the drawback that it's also a gas, but much easier to compress and has a much higher volumetric heating value than hydrogen.
And
So
already a whole infrastructure for it.
and the
Then,
infrastructure, yeah, we have our liquefied natural gas, of course, currently a huge topic. So there we have infrastructure. However, we still need some energy to achieve these low temperatures. And if we just want to burn the synthetic natural gas, then of course this would be a proper way, a proper solution. But if we want to use methane as a hydrogen carrier, it's not just about the hydrogen storage density, but it's also about how do we get the hydrogen out of this molecule. So we would need to apply like conventional steam reforming technologies, and these need very high temperatures. So basically, you would have to burn something to reach these temperature levels.
yeah.
This could not be done via heat pumps or electrical heating. At least this is a research topic at the moment, let's say it that way. This is a big advantage for methanol and also for dimethyl ether, because these molecules we can steam reform already at much lower temperatures, at much milder conditions. Yeah.
And the dimethyl ether also is liquid hydrocarbon made from methanol, or are there direct routes to DME?
Actually, you usually go to methanol first as platform molecule, and then from methanol you go to dimethyl ether. So basically, that's a dehydration, and then you obtain dimethyl ether. This is used to be quite a challenge in literature because, like these gas phase processes, you need to separate methanol from dimethyl ether. That was a topic. You had an equilibrium limitation there. But my colleague Malte Gierse was researching on a new process for DME synthesis, which is based on reactive distillation. So basically, we can enter the distillation column just with raw methanol, so a mixture of water and methanol. And top product will be dimethyl ether, and bottom product will simply be water. And this process to convert methanol to DME is prospectively getting much, much easier. So we are currently in our technicum making experiments to scale this synthesis up, check the stability of the catalyst and so on.
Yeah, interesting.
So that's one molecule you can obtain from methanol, but
Yeah.
of course methanol is so much more. Yeah.
It's one more step. So the advantage of DME, as I understood, is that it can store more hydrogen in the same volume.
Exactly.
Right?
Yeah. Yeah. So especially when you apply steam reforming to these carbon-based molecules like methane, methanol, DME, then you get an additional molecule of, or you get additional molecules of hydrogen out from the water you introduce to the steam reforming reaction, basically. So this is of course not for free because steam reforming is always an endothermic reaction. But if you calculate the specific reaction enthalpy per molecule of hydrogen you obtain, then the energy input is way below water electrolyzer or something.
Oh, okay.
So there you can save a lot of energy at the hydrogen consumption side. And this has another benefit because in all of these synthesis processes, so when you come from CO2 and hydrogen and convert it to methanol, to dimethyl ether, or to methane, you produce a lot of water. For methanol synthesis, for example, from CO2, you produce one molecule of methanol, one molecule of water. And this water you can, of course, separate and lead back to the electrolyzer. So when we talk about the locations where we are going to produce these hydrogen carriers in the future, we will probably be in areas with a lot of sun and not a lot of water. So not the areas like Europe. We do not have a lot of sun. We have a lot of rain here. So basically very dry areas. And there we need to keep the water or decrease the water consumption of this reaction. And this is one pathway. And one benefit you have with these carbon-based hydrogen carriers compared, for example, to ammonia. Ammonia, which is nitrogen-based, you cannot steam reform. So there you really only get the hydrogen out you transport. And you consume the same amount of water at the consumption side as you would if you would just produce hydrogen and ship it to Germany or Europe. Yeah.
Also, you just mentioned that you would need less water, but that is because the steam reforming basically is done, for example, in Europe when we consume the hydrogen and you get part of the water back while doing the methane or methanol synthesis from the CO2 that you use, right? Okay.
Yeah, so maybe this point wasn't clear. So of course in Europe, currently at least we have plenty of water, I would say, compared to South America or Africa. So here we could use our fresh water and add this to the steam reforming. We would not transport the water over the ocean.
Yeah.
We would just transport the hydrogen carrier.
That piece of water is then basically used where we have enough water in Europe.
Exactly. No.
And when we now talk about methanol, we already said it can be used for fuel. What other uses for methanol?
Yeah, methanol is currently used directly as a fuel in a quite high amount in China. So they blend, I guess, up to 20%, maybe even more, into the usual gasoline. So that's actually a curiosity when you hear of that the first time. Why does Europe not do this?
Yeah.
Well, Europe imports basically all of its mineral oil. And this is what the Chinese actually don't want to do. So they want to be globally independent, geopolitically independent. And so they also do not have a lot of mineral oil. So actually, this is quite similar to the situation in Europe. And they use their coal, gasify it, make a syngas out of that. And then with the syngas, they produce methanol as the first platform molecule. They can use the methanol directly, of course, as a fuel. They can also export it when the world market price is high. They can directly export it to nations that need it. But of course, they can also go further, like do basic conversions to formaldehyde, other base chemicals, which they again need for their polymer industry, for example. And what they also did since around 2010 was methanol to olefins. So methanol to olefins is actually a process which is not very economic, I would say, compared to just drilling a hole and getting mineral oil out and refining that. That's of course much cheaper than methanol to olefins. But here again, China wanted to be independent from the oil market. And when the oil prices are high, the Chinese economy is actually pretty relaxed because then they simply ramp up their MTO capacities and produce all of their hydrocarbons with these facilities.
Yeah, because the olefins are basically the basis for the whole petrochemical industry we already have. And then all these very well-known processes can be used to make basically the whole range of chemicals that are used in the world.
Yeah, exactly. Because in case of China, a super dirty process when they do it. Coal gasification is one of the most dirty processes in the world. And the methanol produced from coal gasification has a huge carbon impact or CO2 impact. So this does definitely play a huge role also for global CO2 emissions. But also there's something positive about this because China kind of implemented this MTO technology and increased the technology readiness level in the last decades quite a lot for these technologies. And now there's some scientific know-how on that. And when we talk about the future, then we can, of course, use this know-how to start from green methanol, not from black methanol, as I call this coal-based methanol, and then could have CO2 neutral hydrocarbons and use these for aviation industry, for example.
Yeah, that's really interesting that you can basically use this very dirty technology to then use it on green methanol, and then the whole story changes, because with the green methanol, there's basically, since you take CO2 from the air or other processes which emit a lot of CO2, you can basically decrease actually the amount of CO2. If you would make plastics out of it, then you could even store this CO2 somewhat for a long, long time. And this is interesting because it's more or less independent of where you get the methanol from. So you can actually now benefit from this technology that was developed for a completely different reason, that coal needed to be turned into chemicals.
That's a very important point you mentioned here. And this is maybe also a fact why I like my job and the area I'm working in, because this whole power to X area is mostly based on very old technologies. So when we talk about ammonia, this was like the first high pressure, high temperature synthesis. Methanol was the second one. So methanol synthesis is now 102 years old. So this is a super old synthesis. And when I started my PhD, I actually wondered, okay, what can we do better about this old synthesis? Like everything was invented there. There's so many companies out there who are like spending a lot of R&D budget into increasing the efficiency of methanol synthesis. But then when I actually looked into CO2-based methanol synthesis, which is entirely different than this fossil process, then it becomes interesting. So with these details, then you have to deal, and this is what we are dealing with here in our research group. So for example, these old processes, they were all based on coal or natural gas. So basically, let's talk about natural gas. Maybe you drill a hole, you check the composition of the natural gas, you customize a steam reformer plant, build it on top of the borehole, somewhere in Africa, for example. So then you can convert the natural gas to methanol, which you can transport super easily, and you ship it all over the world as base chemical.
And it is already traded as a commodity, right?
Exactly.
Methanol has a huge market.
Exactly. So there's this thing called stranded gas. This is, for example, in Equatorial Guinea. They have a huge methanol synthesis plant because they have a huge natural gas depot and they don't know what to do with this natural gas. So yeah, they make methanol from it and then ship it all over the world.
Oh, interesting.
So that's a business idea,
Yeah.
or was a business idea. Yeah, and all of these processes, they run steady state because
Mm,
once the plant is up and running, then basically the operator will never turn this plant down until the catalyst is, for example, worn out and you need to
yeah.
replace it. But usually they run 24/7 on full load.
Hmm.
And when we now talk about power to X, we are usually based on renewable hydrogen,
Hmm.
which is based on renewable power. And we do not have like a steady power supply because, for example, there's no sun, there's no wind whatsoever. Then we have to be able to turn down our electrolyzer pretty quickly.
Yeah.
And this is not a problem on current state of the art. Like there's very dynamic electrolyzers already today. But the problem is the next steps. So when we convert this hydrogen to methanol and also to like follow-up products,
Hmm.
downstream products, then we need to make the synthesis running dynamically, at least the first step, which is the methanol synthesis, because then we have a liquid product we can store in a buffer tank. But yeah, hydrogen is such a light gas that it's super expensive and difficult to store.
Yeah.
So we would not want to store a lot of hydrogen at industrial production site.
I guess some part can be buffered that you don't really have like directly connection electrolyzer to the methanol plant. But as you said,
Sure.
storing hydrogen needs compression, and that, especially for hydrogen, needs a lot of energy. So I guess you want to avoid that as much as possible, right?
Exactly. So we need to define the technical limits of how dynamic can our methanol synthesis process go.
Hmm.
So if it could follow the dynamics of the electrolyzer, then it would be super dynamic.
Yeah.
I don't expect that this will be possible in the near future.
What are the main problems? Uh, Actually, the methanol synthesis, the catalyst.
That's a good question. That's a very good question. And we thought, first of all, that the catalyst would be a huge problem,
Hmm.
and probably it is. So there's still studies missing where you apply a fluctuating load over a long term on methanol synthesis catalyst and then compare it to a steady state catalyst.
Hmm.
So does it age quicker than a steady state catalyst? Can I say it like that? I think yes. So there's long-term studies missing at the moment.
Hmm.
That's maybe the problem.
I guess that also comes from that where all these optimizations that were done before for the coal process, they aimed for the steady state, and now we're looking into this dynamic process, which is then new with similar concept, but with new challenges.
Yeah, exactly. So nobody actually was taking care about the temperature profile inside the methanol synthesis reactor, for example, so much.
Mm-hmm.
Of course, this is a topic. Let's maybe first introduce a methanol synthesis reactor.
Mm-hmm.
There's different types, but let's talk maybe about the steam-cooled reactor, which is like the industrial standard. There you have a tubular reactor, so many, many tubes, maybe 9,000 tubes, which are 7 meters long, have an inner diameter of 5 centimeters, and they are filled with catalyst.
Mm-hmm.
And outside these tubes on the shell side, you have circulating water, which is evaporating.
Mm-hmm.
So you're generating steam from this reaction, from the heat of the reaction.
Maybe let's go back a step and quickly introduce the basics of the methanol synthesis.
Yeah, so basically methanol synthesis is an exothermic reaction which is equilibrium limited. So yeah, you cannot get 100% conversion within a single pass through the reactor, even if you want to.
Mm-hmm.
It's volume decreasing and exothermic. So thermodynamically, you would need low temperatures and high pressures to make this shift the equilibrium towards the product side and get something like an almost full conversion. Unfortunately, this low temperature doesn't work because the catalyst is not active below 200 degrees Celsius. So we need an increased temperature inside the reactor, and usually temperature is between 200 and 300 degrees Celsius. And to counterplay this higher temperature, we need to increase the pressure of the synthesis. So that we can achieve a significant conversion in the reactor at these temperatures, we need increased pressures, which usually are between 50 and 80 bar. And even then, we probably have per pass conversions between 10 and 20%. So what happens basically in the methanol synthesis process, you condense out the condensables. So this is basically methanol, water, and condensable side products, which are not much. Selectivity is super high. And the uncondensed gases, they are recycled back to the reactor so that you can obtain a full conversion.
So you have a loop between the gas phase, which the condensables are taken out, and that is fed back. From what I remember from a lecture in the university is also that they have two reactor concepts where they have basically one reactor which does a lot of the conversion, and then you have basically a second reactor which converts less amount but more, like brings it more to full conversion, like this Lurgi methanol process.
You can control the thermodynamics, of course, a bit by temperature. So if you first have, for example, an increased temperature, then you have very fast reaction kinetics in the first reactor. And if you're in the second stage or second reactor, you have lower temperatures, then you are like in a better equilibrium yield. But of course, you need more catalysts to get to this equilibrium then, because the reaction rate is slower.
Yeah, the temperature control is very important in these kinds of reactions. You have mentioned that this tubular reactor design is used with these 9,000 tubes to basically keep the reaction temperature lower, which would increase on its own. And you were saying that you can get a lot of steam out of the reaction.
So you're generating a lot of steam with those, and due to this diameter of 5 centimeters, you do not have an ideal isothermic temperature profile. So there's actually, some people call it isothermal reactor, but I rather used to call it polytropic reactor because you have a heat removal to some extent, but not all of the heat, especially in the first zone of the reactor where the syngas is super fresh. You are far away from the chemical equilibrium. There you have a very high reaction velocity and, of course, as a consequence, a very high amount of heat produced. So there the temperature rises.
There are then hotspots in the reactor, and they do harm the catalyst?
That depends on the syngas composition. So that's also a huge question I covered, not only me, but also other researchers covered in their research, but also I did analyze this in my PhD. So how does a certain gas composition affect the temperature of the hotspot? So you usually have a cooling temperature between 240 and 260 degrees Celsius. And the absolute maximum temperature you should achieve in this hotspot should not exceed 280 to 300 degrees Celsius. So if you exceed this temperature, then the catalyst starts sintering inside the hotspot, and yeah, basically it dies pretty rapidly. So this is a border not to cross, I would say. And for this steady state conventional process, there has been a lot of measurements from industry, which are not known to the scientific society, of course, because this is all highly confidential. But also there has been a lot of research on that. How high is the hotspot inside the reactor?
Maybe we can go again one step back to compare this new process to the conventional process. I think that the conventional process is from syngas, so a mixture of CO and hydrogen, and the newer or hydrogen-based processes are based on CO2 and hydrogen.
Yeah,
explain?
I can just explain again this conventional syngas. So the conventional syngas has basically a lot of carbon monoxide. This was what you said correctly, but also there's always a bit of carbon dioxide in the syngas
Hmm.
because without the carbon dioxide, the reaction mechanism could not get started
Hmm.
actually. Because at the moment, at least, this is still under a huge discussion in the scientific community, but at the moment, people say that the methanol is not produced from direct carbon monoxide hydrogenation, but rather from CO2 hydrogenation. So CO2 plus hydrogen reacts to methanol and water.
Hmm.
So with the conventional syngas, which is mainly carbon monoxide and hydrogen, where do we get the CO2 from? And this is where the water gas shift reaction comes into play. We need the water produced from the CO2 hydrogenation, and we take the carbon monoxide from the syngas, and then we produce hydrogen and CO2. And with these two gases, we can then do the CO2 hydrogenation.
Hmm.
So basically, it's just these two reactions, most probably at least. So as I said, this is under discussion. But yeah, this is a lot of findings in the scientific literature, and also our own findings indicate that it's just these two reactions mainly. And yeah, the difference between this conventional gas and the green syngas, which is based on CO2 and hydrogen, is basically that in the green syngas or the power to methanol process, you do not have carbon monoxide.
Hmm.
So there you have the reverse water gas shift reaction, basically,
No.
because you have a lot of CO2, a lot of hydrogen. So what's happening is basically you produce water and carbon monoxide. And the carbon monoxide is not a big problem because this can later be converted, recycled to the reactor and converted to methanol again. The problem is rather the water because in this reverse water gas shift reaction, you obtain a lot of water and
Hmm.
in the CO2 hydrogenation, of course, as well. So basically, yeah, you are having very high partial pressures of water, and this was not the case for the conventional synthesis. So this is basically a challenge besides this dynamic aspect, another challenge for the catalyst, that it's subjected to very high water partial pressures, especially towards the outlet of the reactor.
Hmm. Interesting.
And yeah, basically these are the two main challenges. You have a dynamic operation and you have high water partial pressures. When it comes to the temperature of the hotspot, this is not as critical because the exothermic heat of the CO2 hydrogenation is much lower than the exothermic heat of CO hydrogenation. So if you
Hmm.
just look at the overall reaction equation, so the hotspot does not rise as far, but the combination of, let's say, increased temperature and high water partial pressures still damages the catalyst. So this is something you have to take care of.
Hmm. And also, I assume more water makes it more difficult to have the purification after, or is this then
Mm,
not that much of a problem?
well, the water, of course, you have to get rid of in the purification section, which is usually a distillation. Mm, But I think the bigger problem there is that the water also kicks in when you look at the chemical equilibrium. So the
Uh,
water inhibits or decreases the equilibrium yield of the reaction,
yeah.
and it also inhibits the reaction kinetics of the catalyst
Hmm.
because it's adsorbed on the catalyst surface and it basically strongly adsorbs on the catalyst surface. So the reaction kinetics, they get much slower, and to
Hmm.
produce the same amount of methanol from a CO2-based synthesis, you would need much more catalyst compared to a conventional synthesis. So this is also a bit of a problem.
Just more catalyst, or would this directly mean also a larger reactor, which is
As a
usually much more
consequence,
expensive, right?
this means that you would need also a larger reactor or a different reactor concept.
Hmm.
Of course, you can also think of other reactor types like adiabatic reactor
Hmm.
types. But yeah, this is a huge story about reactor design. But the kinetics are slower, and this is, of course, when you look at these key indicators like space-time yield, for example, this is a much lower value for CO2-based synthesis than for the conventional pathway.
Hmm.
So there's a lot of research going on to increase the activity of the catalyst for CO2-based methanol synthesis and also to increase the stability
Yeah.
of the catalyst, the long-term stability.
If-
And this dynamic operation is, of course, also a topic the catalyst producers are very much interested in. So how does the catalyst produce and react when you apply harsh load changes to the reactor, which you would usually not have in a conventional plant? And yeah, this is basically what I measured, but also described during my PhD. And there we actually found out that the reactor is not, I would say, it's not evil, it's not unstable,
Yeah.
right? When you do a load change in a methanation reactor where you have a lot of exothermic heat, then you could come to the point where it simply lights off. You cannot get the heat out of the system, and the temperature just increases very harshly.
From what
For
range
methane,
to what range did you, from like what load to what load did you change?
let's say I manipulated the load of the reactor for plus minus 100%.
No.
No,
Okay.
plus 100 minus 50%. So basically, the measure there is the gas hourly space velocity, at least the measure which is used for methanol synthesis. Of course, there's also the weight hourly space velocity, but let's talk about the gas hourly space velocity. In conventional steam-cooled tubular reactors, this is around 10,000 per hour. So this is calculated by, this is just an indicator, right? An abstract indicator. So it gives you the amount of gas at norm conditions. So let's say cubic meters per hour divided by the reactor volume. So just the empty tube,
Okay.
also there, cubic meters, and then how often do you replace the reactor volume by the syngas? And if this happens 10,000 times per hour at
Okay.
atmospheric
Yeah.
conditions, which is not the case because we are talking about pressures between 50 and 80 bar, then this is a gas hourly space velocity of 10,000 per hour. This is like a standard condition for an industrial reactor. And I manipulated the gas hourly space velocity down to, let's say, 5,000 per hour, for example, within one load change. But at the same time, you can also change the CO2 ratio at the inlet because we have this reverse water gas shift reaction. So there's always a bit of carbon monoxide produced inside the reactor. And the unreacted gases are recycled due to the equilibrium limitation. So we always have some carbon monoxide also in a CO2-based process.
So you
And
had a one-step reactor. That. Yeah.
exactly,
Okay.
once through reactor, but I dosed carbon monoxide as well as a feed to basically model this original gas composition in an industrial process. And if you manipulate the CO2 ratio, then things become very funny because if you have a lot of CO, then the reaction is very exothermic, so the temperature rises. If you're at the same time decreasing the gas hourly space velocity, then the cooling concept basically gets worse because the heat flux Q dot is the heat transfer coefficient times area times temperature difference. And if you decrease the gas hourly space velocity, the reaction occurs on a like in just in the beginning of the reactor. So you basically decrease the heat transfer area you have to cool your reaction. So then also the hotspot increases.
Because the whole reaction mixture is moving slower but producing more heat at the same time. Is that right?
Exactly.
Okay.
Basically, this initial reaction, you have a very fast reaction at the inlet of the reactor. This occurs on a much shorter piece of the reactor tube. So you need to extract a lot more heat per catalyst volume, and this is not possible. So then the temperature increases also. And if you play around with the gas hourly space velocity and the CO2 ratio, then things can become very interesting. So temperatures can rise pretty high. This is, of course, not always a critical case for CO2-based loop processes because when you're talking about a loop process, then these load changes, they wouldn't occur from 1 second to the other, but you're always recycling unreacted gases. So if you have like a part load step, for example, in the makeup gas of the synthesis, then the load transition is much slower than in a once through setup. But I looked at the extreme cases, and even for these extreme cases, I found out that there's no like intermediate hotspot. Basically, you can describe the transition from one load point to the other, at least for the catalyst I tested, with the two steady states. So the steady state before the load change and the steady state after the load change. And the transition does not have a lot of surprises, let's say. There's no intermediate hotspot which exceeds the final hotspot. So yeah, one result was that it's enough to accurately model the steady states, and then you at least are safe on the temperature side. Yeah, that you not exceed the critical temperature.
Yeah. And that also influences the reaction selectivity, I would guess, or is the selectivity not really changed? The reaction.
Selectivity of methanol synthesis is a topic. It's also a huge topic because you need to purify the methanol in the end. So selectivity for methanol synthesis is above 99%. So a very high selectivity, but the side products you produce, which are ketones, like higher alcohols like ethanol, propanol, they can be critical when you want to separate them from methanol. And yeah, if you want to sell a chemical grade methanol to your customer, then you need to make sure that it has some quality, that, for example, ethanol is below 10 parts per million. So, and of course, water, you also have like a certain threshold you should not cross, and for the other compounds as well. So, you definitely need to get rid of the side products. The good thing here is when you come from a conventional syngas with a high CO content, you produce much more side products than when you come from a CO2-based syngas. So this is basically also what we published last year.
Why is
we,
that? Can you say that? Or is this known?
Actually, it's not known. That's a super interesting question. There was some literature data indicating that higher CO2 contents in the gas decrease the amount of side products, but this was very few literature data, and we wanted to validate this. So we did it in our project Carbon to Chem and published this last year. So we did a study where we varied the syngas composition, the feed gas composition of the reactor in a mini plant process setup over a super wide range. So we not only varied the CO2 content, but we also varied the recycle ratio of the process. We varied the stoichiometric number, so the amount of hydrogen compared to the carbon oxides, the inert gas content, the pressure of the synthesis, and also we measured the hotspot temperature and the time on stream of the catalyst. And yeah, we did a correlation analysis of this. And basically we found out that the highest correlation we got with the CO2 content of the feed gas.
So the CO2 content has the highest influence on the amount of side products?
Exactly, yeah. So that's at least for the higher alcohols, for paraffins, for ketones. Methyl ether is also one side product. So for the condensable side products, we could definitely observe this. So we only looked at the condensed phase. This is a bit of a weakness. It would be nice to also analyze the product gas directly behind the reactor, but from an analysis point of view, this is pretty difficult because you have super low concentrations of these side products. But yeah, in the end, they play a role because you have to, as I said, get rid of those. And this can also decide whether you need one distillation column to only separate water from methanol, or whether you need a second distillation column to get rid of, for example, ethanol. Yeah.
So you could change the CO2 content and then get so little of some of the side products that you could basically use one distillation step less, even?
Well, that's up to the modeling people. We are modeling this also a bit. We are looking at the separation of methanol from the crude methanol. But the results we measured really indicate that the amount of most critical side products decreases almost to zero when you increase the CO2 content to 100%.
That's great news for the green methanol
Yeah,
synthesis,
that's
right?
good news. This was basically also already a finding in the 1990s, but this was really now confirmed by our measurements, which were much more comprehensive. So a huge data set, and also there's some trend lines we also use to calculate the raw methanol composition. So when we now look at a certain methanol synthesis process, maybe not based on CO2, but on biomass gasification, where we have to some extent also carbon monoxide in, then we can now estimate how would the side product composition be, how would the downstream processing have to look like. And when we talk about downstream processes, for example, DME synthesis or methanol to olefins, then of course we can investigate what happens when we introduce raw methanol into this next process step. So we can calculate our composition of our model crude methanol and then make experiments. Does it deactivate, for example, the DME synthesis catalyst in the next step? Or does it somehow influence the composition of the MTO mixture?
So could you do even like two-step reaction where you basically skip the whole purification in the middle, so that you basically have
Yeah,
two reactors with two reactions, but you just feed the crude from one into the other?
that's one idea we are currently following with dimethyl ether, the DME synthesis. As I said in literature, this whole process was super difficult because first you purified the methanol the crude methanol, that you only have methanol and no water left. And now with this reactive distillation, we want to feed the crude methanol directly into the distillation column. And of course, then it becomes interesting. What do the side products do with the catalyst in there? Do they lead to a rapid deactivation or not?
In my PhD, I also tried to do some tandem catalysis, but that was on a homogeneous catalyst. So there, I guess it was a bit easier to see what all the species are and then connect those two reactions. It worked to some degree, but to get to an industrial scale or scale it up really, then a lot more research is needed to really understand where all these products come from and how to purify that in the end.
Yeah, same here. So we would like to have like a follow-up project where we really investigate the mechanisms of side product formation. So does this actually come from the catalyst, or does this just come from the reactor tube or some other equipment, maybe some impurities inside the catalyst? This would be super interesting, and also to see whether the side product composition changes over time. So when the catalyst ages, the performance of the catalyst changes a bit. So usually it decreases. And it would also be interesting to see how this deactivation of the catalyst and the side product formation influence each other. Because when we plan a chemical plant, we cannot just plan it based on the time on stream zero performance, but we have to plan it actually what's happening end of run, end of the lifetime.
Is there a correlation already visible that you can say that the older the catalyst is, the more side products you have, or is it just less activity and you produce less methanol?
No, this would be a nice project idea. So this is a thing we would like to investigate, but of course you need a long-running project because these deactivation measurements, they are very comprehensive. So they would take for one run 1,000 hours probably, and you could probably parallelize it with different working points. But we also found out that at every load point, gas composition, the catalyst deactivates in a different manner. So either you have more thermal influence or you have more water hydrothermal influence. You could also have a poisoning influence, for example, when you come from biomass or when you have some oxygen from the electrolyzer. So there's a lot of work to do in terms of deactivation. Yeah.
And also in terms of catalyst, you used one type of catalyst. Do you think there, with maybe newer catalyst generations, there would be different kinetics, or do you think it can be to some degree be transferred to other catalysts as well?
Well, of course, when the catalyst recipe changes, the active sites of the catalyst change, and the reaction kinetics change. So this, of course, has an impact on the kinetic model as well. So basically, when you come with a new catalyst, you need a kinetic model to describe what's actually happening when you put this into a plant. So of course, the off-taker of your catalyst would like to have an assurance that this catalyst is working, active enough, or even more active than a competitor catalyst. So yeah, this is of course a huge question at our institute because Fraunhofer does applied science. We usually use industrial methanol synthesis catalysts. So the catalyst manufacturers, there's like plenty companies doing catalyst development for methanol synthesis.
Do you directly work with those companies together?
Yeah, this is definitely part of our business model. We collaborate with them, of course, on a highly confidential basis. So I can also not tell you what the difference between different catalysts, industrial catalysts is, even though this is a super interesting topic to see, to observe. But of course, we collaborate with these industrial companies. They are invited to come here, give us their catalysts. We do kinetic measurements, see how the catalyst behaves under dynamic conditions, and can also derive a kinetic model for this catalyst. And then we can at least compare it to literature kinetic models, for example, and see whether this catalyst is better or worse than what's already there. And yeah, there's a lot of catalyst development going on in academia, but also among the catalyst manufacturers. There's a lot of action in the field at the moment.
Interesting. Because that I think is also a good way to bring the results from academia to the industry, because you're somewhat in the middle and you do the academic research, but then also apply all these knowledge and competence you have built up in the whole group to then also apply that to the industry problems you get from your partners, I guess.
Yeah, exactly. So that's also a nice part of my work. Fraunhofer actually bridges the gap between the research, the basic research from the universities or the Max Planck institutes, and the research which is done in the industrial companies. Industrial companies, they usually pick research up when it's at the pilot scale, and then they try to implement their own IP and make their own developments on top of this. And universities, they, yeah, at least in chemistry, usually use very small amounts of catalysts and very small scale setups under super ideal conditions. So ideal isothermic kinetic reactors, for example, or screening reactors. And we try to make this transition towards the pilot scale so that industry can directly pick that up and do their own developments there. So Fraunhofer is basically funded by 1/3 from public money, so directly, and the other 2/3 are project funding. And this project funding, again, half of that is supposed to be publicly funded projects, and the other half is supposed to be industrially funded projects, so direct projects we have with industry. And this is also one indicator every group the Fraunhofer Society has to show. So is our research relevant for industry? If yes, then you could say then the industrial share of your money is in the goal share, which is around 33%. But on the other hand, of course, there was this hydrogen hype. You just mentioned it. When there's a lot of public money in the game, then it's super difficult to obtain money from industry, because industry is also, of course, also part of these publicly funded projects. This is much cheaper than a direct research contract. And when there's a lot of public money in the system, then it is utopic to get the same amount of money from industry. Yeah. It's what we struggle with.
Also, probably that the German chemical industry was a bit struggling in the recent years. That probably also contributed to lower industry projects, or do you not see that they still invested in research?
We definitely see that, but this is not just a phenomenon of the last years. This is also a current phenomenon.
Yeah.
So there's chemical industry is struggling at the moment, and we see that the projects which usually would make sense from like our perspective to the companies, they are not coming because they say, well, we cannot afford it at the moment. We need some more time. There's some reconsiderations whether we carry on with this business unit. So yeah, there's a lot of negative activity, I would say, going on where the R&D budgets in the industry are shrinking.
Yeah, because the money comes later. You don't instantly get money from research usually.
Exactly.
But on the other hand, I think from our discussion, the whole research into new technology, especially green technology, is still, due to probably also governmental funding, still thriving. Or
definitely also it becomes difficult at the moment with the publicly funded money. But I hope that this will get better soon. So there's a lot of potential, of course, because this energy transition thing is one of the core targets, I would say, of our policymakers. So they definitely need to fund this and will carry on funding this. So compared to other research disciplines, I would say we are still in a good shape.
And also they want Germany to be one of the first movers, I would say, and be leading in this all green technology. So for that, we need research.
But that's on the same hand, you have to say that our institute is shrinking at the moment. So it's really shrinking because there's not enough publicly funded money and not enough projects in the pipeline. People have to leave R&D and search for another job. So the situation for research in Germany is not as easy as it was maybe 2 years ago. 2 years ago, like this was, at least for my field, this was super easy, and now it's becoming a bit more difficult.
Yeah.
As I said, I hope this will get better, but let's see, let's wait a bit. Like there's some damage done already. There were some projects which were announced and not coming, and now like the partners are gone for good. So there's a lot of connections that were just destroyed by the last 1.5 years.
Yeah, but with the new government settling in, I hope this will change to the good. To, as I said,
I hope
keep
I hope they
Germany
will
in
have
the
their
leading
household.
position.
Or get
With
it back
green
into
tech.
a leading position, because we also have to say that other countries like China, they are not sleeping. They are doing high quality research. Meanwhile, this wasn't the case maybe 10, 15 years ago, but today they are really like pushing the technologies they want to implement. And this is, of course, also for the hydrogen technologies, a huge challenge for our government to speed up their funding mechanisms so that we can still be on top and not like a dying giant in this hydrogen technology field.
So is there one topic that we didn't talk about today but should?
Another point I would like to highlight that basically these loop processes, they are like a general thing for most of the power-to-X, the basic power-to-X processes. So when we look at methanation, when we look at DME synthesis, we also do not have a full conversion. When we look at ammonia synthesis, we also have a recycling of uncondensable gases. So there actually ammonia synthesis and methanol synthesis are quite close to each other. And of course, one way to separate these products is condensation, but and their innovation comes into place. You can also think of like enhancement of the process. So, for example, by adsorption on an adsorptive, you can also get the product or maybe just one product out. For example, in methanol synthesis, you could try to adsorb water, and then you could also get full conversion. So this is also not an entirely new story. This was researched also over decades. But with this CO2-based methanol synthesis, also this aspect becomes more interesting again. And this is also something we investigate in our group. So how can we intensify these processes under the new framework conditions?
Yeah, interesting.
When we look at these different carbon-based hydrogen carriers, we can steam reform them, like methanol, DME, or methane. We can steam reform them. As I said, methane needs very high temperatures, and methanol, DME can operate under milder conditions, milder temperatures. And this is, of course, also a huge research field we are also involved in. So how mild can the temperatures be for a DME steam reforming? So there we are active at the moment because we want to operate this process with high temperature heat pumps. So at temperatures below 300 degrees Celsius, way below 300 degrees Celsius. And we are now trying different catalysts, also mostly industrial catalysts, industrially available catalysts, and see which catalyst behaves most promising for an industrial implementation. And I want to scale up this process because DME as a hydrogen carrier we see very promising because it has such a high hydrogen storage capacity. We also have a publication on this from 2023 together with the colleagues from FAU Nürnberg-Erlangen.
Yeah, we can also put a link to that in the show notes.
And there we see the potential. However, DME is not yet a commodity chemical on the world market. So this also needs new shipping concepts. And one drawback of these carbon-based hydrogen carriers is, of course, that you need CO2, or at least a carbon source. And there we also see the potential that we could ship the DME from the production side to the consumption side, so to Europe, then do the steam reforming directly at the harbor, capture the CO2 directly from this point source, because there we have a super high concentration. We do not need a lot of direct air capture capacities, for example, which is super expensive then. And we can ship back the CO2 to the origin where we produce the DME.
So a carbon cycle.
Yeah, exactly.
One question to the reforming of the DME with the heat pumps. So with these high temperature heat pumps, it would not be possible to do the reforming of methane or methanol because they need higher temperatures?
No, methanol reforming, steam reforming can also go under pretty mild temperatures, so also below 300 degrees Celsius. But for methane reforming, I mean, if you look at the methane molecule, this is a non-polar supersymmetric molecule. So there you do not have many possibilities to attack this molecule, except you have high temperatures. So for that reaction, you definitely need temperatures exceeding 700 degrees Celsius. And this is way too high for high temperature heat pumps. High temperature heat pumps sounds always like high temperature, but actually they still perform at pretty low temperatures for these processes we're talking about.
Yeah. But would also be possible to use electricity then as an energy source?
Yeah, today in a conventional steam reformer also the methane is simply burned, but not captured, of course. In that case, you could capture it, but of course you would lose part of your hydrogen carrier then. And high temperature heat will be very rare in the future. So we really have to get towards mild reaction conditions with all the synthesis we want to operate. And this is actually like the main motivation behind our process intensification, to drive these reactions to milder conditions so that we can also do it with low temperature heat.
And then electricity as the energy source for the reaction.
Exactly.
Yeah, interesting, because then that's also one more way to electrify also the chemical industry. There are some processes which are difficult to electrify, I think. And for this, molecules like hydrogen or methanol will be needed in the future. That's why it is also still needed to do more research in these relatively old pathways like ammonia synthesis or methanol synthesis and use them in new applications for new challenges.
Yeah, definitely.
Okay, then thank you very much for being here for this very interesting discussion.
Yeah, thank you very much for having me. It was a pleasure. And yeah, looking forward to the questions raised on this podcast episode. So yeah, thank you very much and good luck with your podcast.
Thanks. If you liked this episode, please follow or subscribe on wherever you are listening. This really helps the show more than you know. Also, if you want to read more about the influence of synthesis gas composition on the purity of the methanol product, check out Florian's publication, which I will link in the show notes. And then thank you so much for listening, and until next time, keep innovating and stay curious.